Good afternoon, my name is Jinhui, and today I'm going to present a reconfigurable rainbow PIV system, which can be used for 3D flow measurement. Fluid imaging in general aims to reconstruct the structures and the motions of the flow. Prior work has been done, for instance, imaging the smoke, the flames, the airflow, and the process of fluid mixture. While these approaches only recover the scalar field of the density, even though optical flow style strategies can be applied to reconstruct the flow velocity field. For example, the follow-up work of the fluid mixture, while in this case, the high-frequency information of the flow will be lost. Current state-of-the-art method to fully characterize the 3D fluid flow velocity field is to using the tomographic particle imaging velocimetry. It is implemented by insert small tiny particles into the volume and set up a multi-camera system to view from different perspectives and reconstruct the particle distributions by means of computed tomography and then reconstruct the velocity field using correlation-based algorithms. Over the decade of development, TOMO-PIV has become a well-established technology, while there are still several limitations for this method. First, setup and calibrating the multi-camera system is complicated and requires a amount of efforts. And also, the depth of field in this system is always limited. Moreover, in some cases, the optical access is limited. It's impractical to set up multi-camera systems, in which case a single camera approach would be preferred. Last year, we proposed a rainbow PIV system, which makes use only one camera and fully reconstructs the 3D velocity field, flow velocity field. The general idea is that we color encode the depth of the particles, and then the 3D motion of the particles can be tracked by combining the 2D spatial change and 1D color change. At first, I will show you an idea about how this project is about. The depth of the particles in the volume are color encoded. A small amount of water was injected from the bottom. The left-hand side videos is a captured video frame, and the right-hand side is a reconstructed path lines based on the captured videos. This is a pipeline for the rainbow PIV system. First, we use the hardware setup to capture video frames, and then we proposed a joint optimization problem for particle distribution estimation and the velocity vector field estimation. And in this, to begin with, I will give you a quick review about the rainbow PIV. We have a white source comes in and passes through the collimator and the linear variable filter to generate a continuum of parallel light planes, such that the distance between the camera and the particles are color encoded. Moreover, we design a diffractive optical element this can perform the function of wavelength selective focus, such that all the light planes will focus on the same image sensor plane. In this project, we make two contributions. We propose a reconfigurable system for arbitrary volume size. It consists of one flexible illumination engine and an adjustable focus imaging system. On the software side, we propose a computationally efficient solver for high-precision 3D particle estimation. To begin with, I will introduce the improvements on the hardware side. These two pictures shows our previous setup and the proposed setup. As I introduced before, that we use a linear variable filter to generate the parallel rainbows, while this filter will consume a considerable amount of light energy. Instead, in the current approach, we replace this filter by two blazed gratings. This image shows how it works. We place the two blazed gratings parallel to each other at the angle of the blazed angle. And so these two blazed gradient can generate parallel rainbows. This system can not only generate more higher light efficient rainbows, but also the rainbow size can be easily changed by adjust the relative distance between these two gradients. And another setup in our previous setup is using the diffractive optical element for wall in focus image. So why we want to use this equipment? Here is the thing. In our setup, the volume is illuminated by a continuum of light planes, so that the object distance for different wavelengths varies. Given this imaging formula, with different object distance and the same focal length, the image distance should be different. That means at one time step, we can only focus on one particular light plane. For instance, focus on the blue particles, the green particles, and the red particles. Well, with the use of the DOE can have the wavelength-dependent focus, such that we can design a specific structure of the DOE to meet the size of the rainbow, such that different object distance will result in the same image distance and capture the wall in focus images. While there is an limitation that if we change the size of the rainbow, we need to redesign and fabricate another DOE. To overcome this issue, we propose an encoded DOE. The idea is that for given transmission function, target transmission function, it can be expressed as a multiplication of two transmission functions. Based on this, we can design a two-layer DOE systems by solving a constraint L1 factorization problem, such that the focal length of the two-layer DOE system can be changed by changing the relative rotational or translational positions between those two DOE. For example, these two patterns are our designed DOE pattern. We keep one pattern fixed and rotate another one. It can result in different length profiles. We then evaluate the proposed imaging system on different rainbow sizes. Since the depth of field of this DOE plus length setting up is not affected by the aperture size, so we choose the largest aperture size for light efficiency. And the middle image shows the middle shows the images captured using the length-only setup. As you can see, the depth of field is quite limited. As you may be aware that we can reduce the aperture size to increase the depth of field. The results of which are showing on the right-hand side is showing that the light efficiency is reduced significantly for both cases. Okay, having discussed the hardware improvement, we then transfer to the software part. Previously, we have proposed a joint optimization problem for these two reconstructions, and in this presentation, we will only focus on the first part. Okay, the general idea is that giving a 2D rainbow image and take a scan of it, the corresponding ground truth 3D particle locations are indicated on the right-hand side. The goal is to reconstruct these 3D locations based on a 2D image. In order to do so, the image formation model should be introduced. In the model, the particle distributions are expressed by a 2D spatial location denoted as X and 1D wavelength information denoted as lambda. And we model the existence of the particles as a function of occupancy probability. We model the imaging process as a set of point spread functions. And we then define the captured image and the spectral distribution respectively. Since the value is illuminated by a continuum of light planes, so the image formation model can be expressed as a double integral operation, where the first one corresponds to 2D convolution, and the first integral corresponds to 2D convolution. And the second corresponds to the wavelength integration, which represents we compress a full spectral image to a RGB image. and we can formulate the convolution to matrix A, and which can be obtained from calibration. And given the 2D image, the goal is to solve this linear system to get the particle distributions. This is an ill-posed problem because we compress the full spectral information to just 3 color channels. A common way to tackle this problem is to introduce the regularization term and formulate a minimization problem. In this case, we encourage a sparse distribution of the particles. So we introduce the L1 term, and this last problem can be solved by well-known ADMM framework. We update the primal variables solving this linear system, and then update the auxiliary variables solving the soft thresholding. And after that, we update the dual variable. In this case, the matrix A, in our settings, the matrix A is composed of the matrix A to each color channels. While with the increase of the system size, it would become expensive to solve this minimization problem. A common way to alleviate this issue is to decompose the original big problem into smaller sub-problems using consensus strategy. In our decomposed algorithm, each sub-problem corresponds to the image formation model with 1 color channel. And the P sub C here means the local primal variables. And all the local variables are constrained by a common global variable Y. And this consensus strategy can be still solved by the ADMM solver, except that we can solve the sub-problem independently and then aggregate the local variables by computing its average. Note that solving this, the linear system of this sub-problem is much cheaper than the original ones. While there are 2 issues arising for this consensus strategy. The first one is over-averaging issue. In our case, the generated rainbow covers a broadband of visible spectrum ranging from blue to red. While for 1 color channel, it only covers part of the observing volume. For instance, the red covers top region and the blue covers the bottom region. That means each sub-problem can only correctly reconstruct the particle distributions within the regions with the referred color information. While if we average the solutions to each sub-problem, will lead to a degraded result. We proposed a truncated strategy to overcome this issue, where each sub-problem only reconstructs the particle distributions within the region with referred color information, and the average are only performed on overlapped regions. Another issue is for the camera spectral sensitivity. We know that the camera will have different spectral sensitivity to different wavelengths. For instance, the green channel of the camera sensor will be effective to wavelengths ranging from 500 nanometer to 600 nanometer, while it will have the peak response at 530 nanometer. While this spectral sensitivity will result in a non-uniform distribution of the reconstructed particles, which are preferred to be placed at the light planes with high spectral response. In order to compensate for this spectral sensitivity, we used a depth-varied L1 penalty term. Specifically, we give larger penalties to the light planes with higher sensitivity and smaller penalties to the light planes with lower sensitivity. We then evaluate our algorithms with regarding to the reconstruction accuracy. We use a matrix of quality factor Q, which is the normalized correlation coefficient between the reconstructed particle distributions and the ground truth. The results are showing on the right-hand side. A solid horizontal line here means a good enough reconstruction. As you can see, that the proposed truncated ADM solver outperforms the original ADMM solvers at all particle densities. And as for the consensus strategies, due to the introduced over-averaging issue, the results are degraded significantly. We then evaluate the execution time of the proposed algorithm. For the ADMM solver, the most expensive part is to solving the linear system for updating the primal variables. And there are generally two types of approaches to solve it. One is cache the factorization using Cholesky decomposition, noted as CD, or we can use conjugate gradient to iteratively update the solution, denoted as CG. For the time complexity for Cholesky decomposition, it's n squared. As for the CG, it has a time complexity of m times the square root of k, where m is a non-zero element and k is a condition number. When the system size is small, the CG solvers always outperforms the CG solvers, while it will increase quadratically. Well, for our proposed algorithm, since we decompose the original big problems into smaller sub-problems, so within the tested regions, the CD solvers always outperform the CG solvers. It can reach up to 5 times speed up over the standard ADMM CG solvers. Okay, in conclusion, in this work, we proposed a reconfigurable rainbow PIV system, which consists of a flexible and light efficient illumination engine, and also an adjustable diffractive optic imaging system. While the limited axial resolution is still a big limitation for our model, in general, the axial resolution is limited by illumination spectral resolution and camera spectral resolution. Specifically, the wider the rainbow is, the finer the resolution it would be, while this axial resolution is more constrained by the camera spectral resolution. Since we represent the full spectral image by only 3 color channels, the metamerism will introduce the ambiguity to resolve the spectral features. Okay, thanks for your listening.
Thank you. We have some time for questions. I was wondering how you're dealing with motion blur as the particle velocity increases.
Yes, currently we are not dealing with motion blur, but it existed in the captured images if the flow is quite fast. But currently we are not dealing with the motion blur because we use quite high frame rate, and also the motion of the fluid is not so fast.
Mm-hmm.
So the particle flow, you're not really concerned with the amount of access.
Okay, scattering, yeah. Yeah.
The intensity of information, it's just color.
Yeah.
Is there
Yeah, that's true.
So the question is there a backscatter from some of the particles that would mask intensity from further away particles?
Well, no, actually, I was thinking on the illumination side.
Okay.
So right now you're just doing only color-based.
Yes. Yes.
So code not just the color but also intensity.
Yes, and as for the scattering, yeah, this is an issue if the particle density becomes large. There will be several scattering issue, but in our tested case, the particle density is not as large as that, as to generate very strong scattering. So we didn't consider it in our approaches.
Other questions? At some point, you started talking about possibly changing aperture codes so that we can have better ability to distinguish between depths,
yeah,
as opposed to standard aperture. Can you talk a little bit more about that?
You mean change the aperture, reduce the aperture size?
No, put some kind of a code that makes it more
you mean
variant to depth.
We didn't. You mean the coded aperture to depth to encode the depth?
Yes.
Yeah, we didn't work on this. Yeah, by now. Yeah.
Right. Thank you very much.
Thank you.
All right. Thank you for the introduction. 1 second. All right. So in this work, we leverage two things that can be found almost anywhere nowadays: artificial light and smartphones. Now, most artificial light comes from bulbs connected to the electric grid. These bulbs flicker at a frequency of 100 or 120 hertz, depending on the country, and their flicker shape depends on the bulb size, type. Now, because different bulbs flicker differently, analyzing scene flicker enables digitally separating images into different illumination components, where each component shows the scene as if illuminated by only a subset of bulbs. Also, flicker analysis enables separating semi-reflections from windows. Moreover, flicker also depends on the electric grid that powers the bulbs. Therefore, for scene bulbs, flicker can be used to recover the electric grid phase and the temporal variation of that phase. Now, if you're not familiar with what a phase is, I'll talk about it shortly. So, in our previous work, we captured scene flicker using a coded exposure camera that we call the A-cam. In this work, we show that scene flicker can be reliably sensed using almost any off-the-shelf camera having a rolling shutter sensor. Our new A-cam has the following advantages over the old one. First, it is untethered to the AC and thus can be used anywhere, not only near an outlet. Secondly, it can accept any optics because it's just a camera, unlike the complicated relay optics of the old A-cam, which limited its image quality and light gathering capacity. These two factors make the new A-cam much faster. So, in a rolling shutter sensor, rows are exposed one after another with a constant delay d. Now, let's denote the image row by r. Thus, if the first row was captured at some time t, row r is captured after rd seconds. Now, d is very short, on the order of 20 microseconds, which causes artifacts when imaging fast motion. But in our case, d has a great advantage. It provides a high temporal sampling rate for the scene's flicker. Depending on the camera, d enables between 200 and 1600 samples per flicker cycle, which lasts 10 milliseconds. This is my son Tom, by the way. So what happens if we try to take rolling shutter images of scenes illuminated by flickering lights? But right before that, let's recall how we captured flicker using the old A-cam. So let's look at a plot showing a periodic flicker for one bulb. So in the old A-cam, each frame sampled the scene at some known time within the flicker cycle. The sampling times were known because the old A-cam was synchronized to the AC grid through a power outlet. To get the flicker sequence, we simply captured frames that uniformly span the flicker cycle. Now, in a rolling shutter frame, the first row starts at some time within the flicker cycle. Then, each subsequent row samples a different time within the flicker cycle according to the inter-row delay. But, unlike in the old A-cam, here the sampling times of the first row are generally unknown. So, per pixel, one frame provides one sample within the flicker cycle, but a sequence of frames provides samples that span the flicker cycle. I will show that by correctly reordering and resampling a sequence of rolling shutter frames, we are able to produce global shutter flicker sequences of the scene, similar to the old A-cam. Now, due to the increased speed and efficiency of the rolling shutter sensor, these sequences can now be rendered in real time. In turn, this enables other real-time A-cam applications, such as unmixing and AC analysis. Moreover, I will show that even a single rolling shutter frame can provide information about bulb AC phases and also be deflickered. Our work joins a vast body of research that used rolling shutter and other coded exposure cameras for various tasks, ranging from 3D sensing to inter-device communication. We will start with a quick reminder about the imaging model under AC lighting. Then we will extend this model for a rolling shutter sensor. Afterwards, we will show methods that use sequences of rolling shutter frames to render global shutter frames. And finally, we will show methods that extract bulb information from 1 and 2 frames. So let's start with a quick recap about imaging on the electric grid. Power plants supply AC voltage in 3 phases separated by 120 degrees. Let's look at phase 0. Different bulbs respond differently to the AC input voltage. Their response is a periodic flicker profile, which we defined as the bulb response function, or BRF. Now, because flicker is periodic, we define the BRF over a canonical time Tcan, which ranges over a circular domain between 0 and delta, the flicker cycle. The canonical time origin is synchronized with the AC voltage 0 crossings. Additionally, we will also use the standard time definition, which we denote by T-abs. So, just to make this clear, absolute time is the regular time we are familiar with, and canonical time is the time within the flicker cycle. Now, connecting identical bulbs to AC phases 120 and 240 causes a corresponding phase shift in their response function. In this case, we treat the scene as having 3 different sources, each with its own unique temporal profile. All right, so now let's look at a scene illuminated by just one source. And let's set this source as our reference source by setting its AC phase to 0. We can always choose one source to do that. Now, the scene intensity at row R and column C is the product of 2 terms. First, the single source image. A single source image shows how the scene would appear in a standard long exposure if only that source was active. More formally, it holds the light transport coefficients relating that source and every camera pixel. And the second term is the source response function we just saw. So in a general scene, the intensity is the sum of contributions from multiple sources, each having its own light transport coefficients, AC phase, and response function. By the way, these light transport coefficients are what we're trying to retrieve when we're doing unmixing. All right, so now let's extend this model for a rolling shutter sensor. So we've seen that in a rolling shutter sensor, the first row starts at some canonical time. Then the inter-row delay produces a diagonal sampling of the space-time volume. This sampling produces a wave pattern in the frames whose spatial frequency depends only on the flicker frequency and the row delay. Now, what happens to this wave pattern between the frames? Well, increasing the canonical time in the equation shifts the BRF backward. In the frames, this moves the wave pattern upward with a velocity of 1 over d. This motion depends only on the canonical frame time and is invariant to both the scene light transport and BRFs. And a general scene is a sum of contributions from all scene sources. So are all rolling shutter frames affected by the flicker wave pattern? The answer is no. If we set the exposure duration to the flicker cycle, the resulting frame emulates direct current imaging. Now, in image regions dominated by only one source, the DC image approximately equals to the source light transport. Now, if we divide our frames by the DC image, we are left with only the vertical wave pattern. This will be useful later. All right, so now let's see how we use this model to render AKM flicker sequences. So what are we trying to do? Our goal is to use a sequence of unordered and unsynchronized rolling shutter frames to render global shutter frames. Now, once we have those, we can use them for all the applications mentioned at the beginning, and with the added bonus of having them in real time. Now, here's the main idea behind our method. For each pixel, a single frame yields one sample at some unknown canonical time. To find the sample canonical time, we must determine the frame's canonical time, which is also the time of the first row. This is the assignment task. Now, a sequence of frames provides samples that span the flicker cycle. So once we assign the canonical times for all the frames, we recover the signal at each pixel. And here is an example result. Here's a video showing 140 frames captured using a smartphone camera. Now, if you look at the wave pattern, you will see that the frames are unordered and unsynchronized. And here is the rendered sequence of 30 global shutter frames of the same scene. So at first glance, assignment seems like a simple task. Why not use the frame timecode supplied by the camera? Well, I tried that, and it doesn't work. This is because of jitter in both camera electronics and AC voltage frequency. Given these problems, we must perform an image-based assignment. We show two assignment methods that fit two types of typical scenes. Here's the difference between these methods. The first method assumes an image region with a visible wave pattern. Using the wave pattern motion, the method provides time assignment frame by frame and is thus suitable for real time. The second method does not require a visible wave pattern. Instead, it relies on an entire batch of frames to work. Thus, it is more general but unsuitable for real time. So let's start with the first. So we've seen that the wave pattern motion depends only on the frame's canonical time. Therefore, by computing this motion per frame, we can recover the canonical time differences between all the frames. This provides temporal assignment for all frames up to an unknown global shift. Now, for some applications, this global shift doesn't matter, and we can simply set the time of the first frame to 0. However, when synchronization to the AC zero crossing is required, for example, in bulb recognition, we can find the global shift if we know the type of one scene bulb and an image region that it dominates. More details about how to do this are in the paper. Okay, so now let's talk about the second assignment method. So what about scenes like this? Scenes of distant emitters don't have diffuse surfaces with a visible wave pattern. So how can we recover the canonical times in this case? Let's look at a batch of frames correctly ordered within the flicker cycle. Now, due to the periodicity of both the flicker and the rolling shutter wave pattern, we expect that two frames that are very close in canonical time should have very similar image intensities, while frames that are separate in canonical time have less affinity in their image intensity. In a two-dimensional space, such pairwise affinity maps the set of all frames to a ring. So, given an unordered sequence supplied by the camera, we find this 2D embedding using diffusion maps. After mapping, the angle between any two frames in 2D corresponds to the canonical time difference between them. So, after we find the canonical times, we still need to estimate the signal per pixel. Well, according to our model, the signal at each pixel is periodic. Therefore, it is natural to present it using a Fourier series. At each pixel, we have m unknown coefficients, and we apply least squares optimization to estimate them and recover the signal. Okay, so we've seen how to create ACAM sequences using rolling shutter sequences. Now I'm going to switch gears and talk about what we can do with only one or two frames. So let's start by removing the flicker wave pattern from a frame using our model. So to deflicker the frame, we apply homomorphic filtering. This means that we first apply a log to the image intensities, then a linear filter, and finally an exponent to get to the flicker result. Now, let's see why this works. Let us focus on image regions mostly dominated by a single source. Recall that in these regions, the frame is the product of the light transport and the flicker wave pattern. In these regions, the logarithm turns the product into a sum. Now, the spectrum of a single log image column shows the spikes that correspond to the flicker frequency and its harmonics. Now we apply a linear vertical filter that blocks these spikes and remove the flicker component. And similarly to the DC image, the resulting image approximates the light transport in the single source region. All right, so now we'll see something rather exciting, that even a single frame is enough to provide information about the AC phases of seen bulbs. So let's start by making two additional assumptions. That we have a database of BRFs and that the seen bulb types are known. Then, let's divide our frame by an estimate of the scene's light transport to remain with only the flicker component. We can do this estimate either by filtering or by additionally capturing a DC frame which approximates the light transport better, in which case we call it a two-frame method. Okay, so now let's do the analysis. Let's look at a pixel dominated by the right bulb and plot the image column intensities around it. Now, let's set the right bulb as our reference bulb by setting its AC phase to 0. If we plot its BRF as a function of the raw delay, we see a shift. Looking at the equation, this shift corresponds to the frame's canonical time. Thus, by finding the shift, we find the frame's canonical time. This is good, but we are looking for the AC phases, right? So now, let's look at a pixel dominated by the left bulb. Again, we see a shift. But since we've already determined the frame's canonical time, now the shift comes from the AC phase of the left bulb, and we can find it. So applying this process per pixel yields a phase map of the scene. Now, in the single frame method here, we used a large Gaussian filter to approximate the light transport. This coarse filtering degrades the estimation result in image regions with non-smooth light transport, while the two-frame method handles these regions correctly. And in the paper, we show how to handle the case where the scene bulb types are unknown. All right, so what about a scene like this? Single frame analysis for emitter scenes. We don't have a batch of frames, and we don't see the flicker wave pattern in a single frame. So what can we do? Again, we want to use only a single image. Let's induce the wave pattern by attaching a star filter to the lens. When aligned with the sensor, the star filter point spread function smears the emitter light in the vertical direction. Now, combined with flicker, this produces the vertical wave pattern that was missing. And we can apply our AC analysis and retrieve the AC phases of the bulb. So, in conclusion, we've shown that imaging on the electric grid can now be achieved using almost any off-the-shelf camera. This makes flicker imaging easier than ever and accessible to anyone with a smartphone. By the way, if you want to see our real-time capabilities live, come to our demo session at the upcoming CVPR conference. Thank you.
You are to the orientation of the rolling shutter. Right now, you're assuming it's a vertical rolling shutter.
Yeah.
Are there any calibrations you have to do? Because even a small tilt would give you the cos theta of that.
So I haven't experienced any problems with standard cameras, including smartphones and machine vision cameras. Actually, with Kyros, we try to apply this method to a 360 camera by warping the rolling shutter back so it would be vertical.
Mm-hmm.
And when this warping is working well, then you can apply the method and it works. But
Okay.
you cannot apply it to an image where the rolling shutter is not vertical.
Okay, so you have to first correct for the vertical.
Yeah.
Other comments, questions? Okay.
So I haven't tried that. It's not going to change anything in the wave pattern. The wave pattern is a global thing that's happening in the room, but I guess you would have to rectify the images. Maybe remove the flicker pattern before, register the images, and then do the exact same processing.
Yes, go ahead.
No, because
The question was, do you need to correct for overall light level, ambient light?
the capturing is very fast, so it takes 1-2 seconds to take many frames. So nothing really happens in these time frames. So I haven't had this problem. No, so again I point the camera to the scene and I capture very fast, and there's not enough time for major illumination changes that come from external sources. Again.
So I mean, if I aim my camera, if I aim my phone at this light, I don't see the rolling shutter effects. Then that's because at the processor level, most of the rolling shutter effects are taken out by a cell phone maker.
So actually, in manual mode,
Right.
if you put your exposure to be short enough, you are going to see the rolling shutter.
Mm-hmm.
I haven't done anything special with these frames.
Okay.
Some LED bulbs have a very low amplitude of flicker,
Right.
and that's why you don't see, for example, in this hall, you don't see the flicker waveform.
Right. So I mean, for these bulbs, you have a very long tail in light fall off because of just the temperature coefficients. And for LEDs, most of them are driven through a DC source. So how often do you see these lights?
So first of all,
So like street lights have sodium, so they have very long decays
Yeah.
as well. So,
So-
which types of lights actually have flicker and which don't?
so every light that is connected to the AC, regardless of whether it's LED or not, is flickering. Think of a bulb as just like an electric device that tries to completely remove the 50 hertz or 60 hertz of the, it's a filter, and there are no perfect filters,
Right.
so you will never get perfect DC.
Okay.
But in some LEDs have very strong flicker, but others have very little. Like
But I mean,
almost
LEDs are
none
not
of
driven
them.
by AC; they're driven by DC.
If they are powered by DC, you will not see any flicker.
Okay. So are there LEDs that are driven by AC?
Or what?
Are there LEDs that are driven by AC directly?
I think most of the LEDs you see in buildings, they are connected to the AC,
Okay. So they have
but they
fluctuation.
have electronics that tries to smooth the signal as much as possible.
Excellent. Any questions in the back? All right. Thank you very much, Mark.
Thanks.
Next, we have towards transient imaging at interactive rates with single-photon detectors, and the talk will be given by David Lindell.
Thanks. So I'm very pleased to be able to present some of our work today, and this is together with Matthew O'Toole and Gordon Wetzstein at Stanford University. And you'll have to excuse my voice because it's a little like the images on this slide, a little hoarse. Okay, maybe a little late in the conference for puns. So, okay. So high-speed imaging has long been of interest to capture things that we haven't otherwise been able to see. And these image sequences captured with only a 500th of a second exposure were captured by a man named Edward Muybridge in the late 1800s at Stanford. And he captured them to answer a question which was, is there a moment in time in which all the horses' hooves are off the ground simultaneously? And indeed, in these images, we can see that that is so. And while Muybridge used this setup, which involved a series of tripwires, which triggered mechanical shutters in the camera array, with modern high-speed imaging, we're actually able to see much more, answer new questions, and understand things in a different way. And so I'll show you an example of a very high-speed image that's captured at essentially 1 trillion frames per second, in which we can actually visualize the propagation of a pulse of light. And this is somewhat a famous image sequence, and we can actually see the scattering off the pulse of light through this Coke bottle onto the surfaces outside the Coke bottle and around the bottle as well. And this type of high-speed image we call a transient image, in which we're actually visualizing the light transport. Now, transient images turn out to be very useful for a number of different applications, including materials classification, understanding light transport and scattering, an application of which I'll talk about a little later in the talk, imaging through scattering environments like fog or murky water, and also 3D imaging, where we're actually measuring the time it takes for a pulse of light to travel to an object and scatter directly back to a detector. With transient images, we not only capture this direct scattering, but we also capture indirect or multiply scattered light events. And these multiply scattered light events turn out to be really useful for doing things like seeing around corners or imaging objects that are outside of our direct line of sight. Now, for each of these applications, we'd really like to be able to handle dynamic scenes with moving content, but so far, transient imaging has generally been limited to long acquisition times and fairly bulky setups. So it's been difficult to actually capture dynamic content. And so what we'd like to do is move from transient imaging to transient videography. And I'll give you an example of what this means. So here we have a really simple scene where we're just illuminating a wall with a pulsed light source, and we can play back a transient image where we can visualize the wavefront that propagates against this wall. And this transient image forms just one frame of a transient video. And so if we capture a transient video, we can begin to interact with the scene, for example, move the light source and see how the light transport changes as a result. And so each of these frames is a transient image that was captured in just a 25th of a second. And over a 5-second exposure, we then capture 125 of these frames, which we can then visualize all at once in this manner. So in this presentation, I'm going to talk about a system we built for capturing transient videos with high acquisition speeds, and discuss some of how the sensors we use, how they work, some of the design trade-offs, also calibration procedures that we use to make the raw data useful for our purposes, post-processing that we can incorporate to improve the quality of the captured results, as well as some results in applications. So there are a number of different ways that we can actually capture transient images. For example, we can use optical interferometric techniques, but these tend to be fairly sensitive to vibration. The transient image I showed you with the Coke bottle video was captured using a femtosecond laser and a streak camera, although these setups are fairly bulky and tend to be quite expensive. We can also use time-of-flight sensors such as PMD-type sensors or single-photon avalanche diodes or SPADs to capture these transient images, although for these and the other methods I mentioned, the acquisition times tend to be fairly long, from a minute to even hours for a single transient image. There has been some efforts to decrease the acquisition time, and including with a streak camera capturing transient images in a single shot, although there are still problems with the bulkiness of the setup and the resulting low resolution of the captured transient images. With PMD-type sensors, we can also increase the acquisition speed, although in this particular work there were restrictions on what we could actually reconstruct in the transient image. And so today I'll be talking about our method using single-photon avalanche diodes, which can run from 1 to 25 hertz acquisition speed. So how does our setup actually work? We take a picosecond laser, which sends very short pulses of light into the scene, millions of times every second, and each pulse will scatter off the scene and send some light to our detector. And for each pulse, our detector has a chance at detecting a single photon event, and when that happens, it generates a timestamp which gives the time of flight of the detected photon. And so a timestamp value of 0 corresponds to the instant at which the pulse is emitted from the laser, and then the last possible timestamp value would be the instant in time before the next pulse of light is emitted. So we're measuring the time of light of these light pulses. And since we're sending them out into the scene millions of times every second, we begin to accumulate these timestamps which record the time of flight of each detection. We can then bin them into a histogram by their time of flight, and this captures a time-resolved view of how much light is actually on the sensor at any given very small amount of time. And we, in our setup, not only have a single SPAD sensor, but actually 256 of these. So what we actually image is a scan line along our scene. And so we capture not one, but actually 256 of these histograms. We can then rearrange these histograms and visualize them as a 2D image, where the vertical axis gives us indexes into the pixel index of our SPAD array, and the horizontal axis records the time of flight. So we'll give you an example of what this image, this 2D spatiotemporal image, would actually look like for a captured scene. So here's a scene that we captured, and you can see the 2D image for the indicated scan line. And the scene is a fiber optic cable that glows when you send light through it, and a picosecond laser that sends these short pulses of light through the cable. Now I've shown you the image for a single scan line, and if we want to acquire the whole scene, we can actually use some scanning mirrors to image a scan line and scan this across the scene. And as we scan, we actually aggregate these 2D images together into a 3D volume. And so there are two spatial dimensions and a time dimension. And then we can play this volume back as a transient image along this time dimension and actually visualize the light as it propagates through the fiber. And so as we look towards transient videography using these SPAD-based systems, where do we encounter bottlenecks, and what are the difficulties as we try to increase the acquisition speed? And it turns out that the bottleneck is right here in the time stamping mechanism. And it turns out that there's a limited number of timestamps that we can actually read out from the system every second or in a given time interval. And for us, that turns out to be about 8 million timestamps every second. And this figure is composed of a product of a few factors, including the frame rate we're operating at, the resolution along the scanning dimension, the resolution along the sensor dimension, and the size of the timestamp buffer. So this is how many timestamps we actually read out at each spatial location. And so this forces us to consider some trade-offs in how we're going to actually operate. We can decrease the number of timestamps that we read out at each spatial location, but then and we can also then increase the frame rate and increase the resolution, but we can decrease the number of timestamps that we read out with a higher frame rate, but since we're reading out a lower amount of signal, the quality of the transient image is going to be reduced. Alternatively, we can increase the number of timestamps that we read out, and since we're reading out more signal, then we'll have a higher quality transient image, but then we have to decrease the frame rate that we're operating at or the resolution. And so these are the types of trade-offs that we have to consider. And so in our case, we choose to operate at two different modes. One in which we acquire transient images at a rate of 25 frames per second, and a higher resolution mode in which we acquire a transient image every second. And so now what are the types of calibration procedures that are required, and what things do we need to characterize about our sensor in order to make use of these data? So we'll talk about just two things in this presentation, sensor noise and the temporal PSF of the system. So you may have noticed when I showed you this transient image earlier that there are these horizontal line artifacts. And these correspond to the dark count or noise in the system. And they form horizontal lines because as we scan our line array across the scene, each pixel scans its own horizontal line. And the noise actually varies across the different pixels. And so the dark count rate, or the rate at which each pixel gives false detections that don't actually correspond to detected photons, varies significantly. So we can measure the dark count rate per pixel and keep track of this and incorporate it into a post-processing framework to try and mitigate these types of effects. We can also characterize the temporal point spread function, or PSF, of the system, which we find to be around 490 picoseconds before processing, and after performing deconvolution, we can reduce this to around 290 picoseconds. So with some of the properties of the sensor characterized, how can we incorporate these into a post-processing framework? And since we're operating at very fast acquisition speeds and low exposure, how can we improve the quality of the captured results? So to reconstruct the transient images, we solve an optimization problem in which we model the log likelihood of the image formation model under Poisson noise, and this also takes into account our calibrated PSF as well as the dark count. And we can place priors on the reconstructed 3D volume or transient image. And so in our case, we use a 3D total variation prior. And finally, the measurements that we acquire correspond to photon detections, and so these are non-negative by nature, so we impose this non-negativity constraint. We solve the problem using the alternating direction method of multipliers, or ADMM, and this allows us to introduce slack variables into the problem and then enforce consensus in the constraints, and basically boils down to iterating over a set of subproblems where each subproblem corresponds to some aspect of our original optimization problem. So there's a subproblem for the deconvolution, Poisson denoising, the non-negativity constraint, and our choice of prior. And what's more is that in this case, each of these has a closed form solution. And so the reconstruction can be fairly efficient, takes about a few minutes to reconstruct a transient image. So I'd like also to show some results and applications. So what can we actually achieve given the constraints on our exposure time and the limit on the amount of data that we can actually read out of our system. So I'll start off by showing some of the results from this higher resolution scanning mode. So this is a scene in which we've placed a statue, and next to it we've positioned a mirror. The raw transient image is shown in the center, and then the post-processed result is shown on the right. And so you can see that through this post-processing we can significantly improve the captured result. You can see the wavefront of light passing across the statue, scattering off the background surface. In the raw transient image, we're only capturing about 20 detections per spatial location on average. And so the exposure time amount of signal we're recording limits the quality we can achieve with this, although this is somewhat mitigated by the post-processing. Now, we can not only just capture a single transient image, but we can capture a video. So if I recorded a conventional video of this scene and I moved the position of the mirror over the capture, you'd see some change in the reflection and its position and some change in the lighting in the scene. But since we have a transient video camera, we actually have a transient image for each of these frames. And so as I'm interacting with the scene, we can actually visualize in the transient images the changes in the light transport, the position of the reflection, the time it takes for things to scatter off the background, and so on. And what's more is that we can actually acquire these at a much more rapid rate, albeit we sacrifice some of the spatial resolution by doing this. So here I'll show a result in which we have 125 of these transient images that were captured at a rate of 25 hertz. And again, we're interacting with the scene and moving the position of this mirror, and we can begin to observe some broad changes in the light transport throughout this scene as we do so. So one application of these data is direct global light transport separation, and I'll illustrate what I mean by this with this scene. So here we've placed a diffuser in front of a cutout T shape. Some of the light that goes onto the scene will scatter directly off the diffuser and back to the detector. And there's also a global component which will scatter multiple times through the diffuser, onto the cutout T-shape, back through the diffuser and to our detector. And if we capture a conventional style image where we're integrating over time, you can see some sort of blobby shape which doesn't really give us any information about the geometry of this cutout shape. However, if we play back the transient image, we can see actually two responses corresponding to each of these surfaces. And what's more is that we can actually separate these out, and in the indirect component or global component begin to see some of the geometry of the hidden shape. So to do this direct global separation, we just use a very simple algorithm, and here I'm showing the measurements for just a single spatial location of the transient image, and you can see the direct and the global responses here. We compute the normalized gradient of these measurements and find where that exceeds some threshold value, and then given the width of our illumination pulse, we have a good idea of where that direct component should end. And then we set the remainder of the measurements to the global component. And so we can also apply this type of direct global separation to depth imaging. So we wanted to explore the effect of indirect light on 3D imaging. And so we construct this scene in which we take some light from the laser directly to the scene through a diffuser, and then also along a longer path and which reflects indirectly onto the scene. And so you can see a slice of the measurements shown below where we have a direct component, again, and an indirect component. And if we apply depth estimation technique to some of these data, the indirect component can actually cause errors in the resulting depth. And so one possible thing to do is to separate out the direct component before estimating the depth, in which case we can somewhat mitigate these errors that can occur. So now I'd just like to talk a little bit about some additional work that we've done along these lines, as well as some considerations as we look towards capturing these at real-time rates with improved quality, and some things that we might consider along those lines. So this is a scene that we captured with a very similar hardware setup. I show a conventional video here on the left. In the middle, this is actually a video of the 3D transient image volume that we capture, shown frame by frame. And on the right is an estimated 3D point cloud, or 3D reconstruction. So to actually capture these types of data, we significantly reduce the number of timestamps that we read out at each spatial location. And with this trade-off, we can then increase the frame rate and the resolution at which we capture the measurements. However, in this scene, there's ambient light. We're reading out a very low number of timestamps. And so as far as how much signal we record, we only get on average maybe a single photon detection from our signal source at each spatial location per transient image. But despite this, we can actually, if we're only looking for the direct component that gives us the depth or the 3D geometry, we can actually robustly reconstruct that shown here on the right, despite the noise in the raw photon counts in this measurement volume that we're reading out. And so if you're interested, stay tuned, and look forward to SIGGRAPH, where we'll be talking more about this project and these results. And so as we look towards real-time transient imaging with SPADs, I think there are a few things that we can consider and that we might also look forward to. So 2D SPAD arrays, we've heard about using these to image through fog, and they're also being produced at increasing resolutions. And so I've already heard of 2D SPAD arrays being produced upwards of 256 by 256 pixels. And these are equally applicable to transient imaging. And using these, we may not need to do any scanning of any sort that we've shown, like we've shown here in this presentation. Also, bandwidth constraints are becoming looser as the hardware technology develops. Again, SPADs are based on CMOS technology, and so it's expected that these will continue to scale in terms of pixel count and the data bandwidth that we'll be able to read out. Sensors are being produced with lower dark noise and dark count, and so it's expected that with improved measurement quality, the processing frameworks can perhaps be simpler or run faster and perhaps allow us to do real-time transient imaging more easily. And so in summary, I've discussed our SPAD-based system for recording transient images, the rapid acquisition with a rapid acquisition rate as we look towards acquiring these at interactive rates and ultimately real-time rates, some of the hardware that we use, how these SPAD sensors work, calibration procedures, post-processing frameworks to increase the quality of the captured results, as well as some of the results we captured and applications. Now, we've also made the data and reconstruction code available online at our website. And so with that, I'll thank you for your attention and conclude. Thank you.
Thank you, David. Questions for David? What do you think about other dimensions that we may crave for, like color and dynamic range and issues like that?
So we can, what are we looking at? Other things like color or dynamic range. As far as color, it's possible to time multiplex color in if you're using different wavelength lasers. Of course, that comes at the cost, if you do it in a time multiplexing way, of decreased acquisition speed. There may be other clever ways to do this faster. And then also for increased dynamic range. So you can operate these SPADs also in different modes. So some SPADs support actually pre-binning on chip into histograms, which allows you to read out many more timestamps, although in this case you usually sacrifice the timing precision. But if you're interested in a larger dynamic range, reading out more data, where maybe you only have a few photons detected in one area, but thousands of photons detected in another area in your image, actually some systems support these types of pre-binning operations.
So if your photon starred in one part of the image, but you actually have abundant photons in the other, you think there's a way for us to deal with it?
Yeah, I do think so. So like I said, you can actually, some of these systems support on-chip methods where you're binning these timestamps without having to send them over a wire to a computer. It's all performed on chip, and you can read out, you can achieve a higher dynamic range that way.
Other questions for David? And what are some tricks on the illumination side? I mean, right now it's, if you go back to Mark's presentation, that actually you can exploit the rolling shutter. In a way, this is kind of an extreme rolling shutter.
Sure.
Right? It's what 8 million rolling shutters effectively per frame, or per second, per frame, I guess, right? So are there any tricks you can imagine in the illumination?
Yeah, absolutely. And we've seen several tricks already in the conference with the epipolar scanning type setups. So for the scenes that we captured, we diffused the illumination over the scene, and then we had a line sensor that we scanned in kind of a rolling shutter type fashion. But you could also consider different ways of positioning the illumination. So if you're just interested in capturing the 3D geometry, you could focus your laser down to a point and scan that. This is more light efficient. You'll be able to image further away because the light is more concentrated. And you could also consider a trade-off where you focus the illumination source down to a line and then image that with your sensor. That will be more light efficient, but then like we've seen in the conference, you'll be capturing these direct illumination paths and the indirect component will be suppressed. So if you're interested in capturing the indirect component, then you need to also illuminate those positions that will give you those paths. So in our case, we spread the illumination out over the whole scene.
I can keep going, so. All right, Ollie, thank you.
So my understanding is that if you have a SPAD array where it has a smaller, the time getting those is less than so what you're saying that bandwidth is increasing, that's something that is starting to go away, is that right? And I guess what I'm saying is like, what if you just use single pixel SPAD detector in the raster array? Would that make it worse? Would it have less throughput than this or anything this?
Okay.
If you can repeat the question, David.
So there are a number of different things. So do SPAD arrays have coarser time binning than like single pixel SPADs? Are the bandwidth constraints just being eliminated over a matter of time with better hardware? And what about point scanning the SPADs? Okay. So it turns out that some SPAD arrays do have much coarser binning. So as I've talked with Guy Satat and Josh Rapp and Vivek Goyal, who've been using these SPAD arrays, it turns out to be the case in this, for the hardware we used, the binning was much finer. So ours was around 20 picoseconds versus maybe a couple hundred picoseconds for some SPAD arrays. So that it appears to be a hardware implementation thing. And my expectation and what I've seen in some of the literature is that work is being done to increase the data throughput and increase the number of pixels. So I think that will just evolve as the hardware researchers improve their techniques. And we can certainly also consider other single pixel techniques, coded masks in front of the single pixel, raster scanning approaches. Although, of course, when you are doing raster scanning, then you're going to have longer acquisition times versus like a line scan or just a 2D sensor. Yeah.
Any other questions? Right. Thank you, David.
Thank you.
So while the next speaker is setting up, how many of you, before coming to this conference, before Friday, had heard about SPAD? Okay. And how many of you are going to
Take that off.
That hand went up really, really energetically up there.
Adapter. You want to take that off, so yeah, we don't want to do it.
Okay, how many of you know about SPAD 3 years ago? Ah, damn. Okay, we got a few. And when you go back, just as a since the last session, you might be probably thinking about writing notes for your group, or telling your children what you learned here, or apologizing to your spouse while you spent a weekend learning about photons and light and optics. So would love to kind of see just shout outs, like some of the words you heard in the last 3 days that you didn't know before you came here, and that were interesting.
Thank you.
Rolling shutter. Just yell out some keywords. Just buying some time here, guys. Come on. Don't be shy. Point light sources. What else? Sorry? Flashlight fish. Yeah. Yeah, the whole animal underwater stuff was mind-blowing. Yeah. What else? That's something I'm sure nobody knew about before they came here. All right. I think we bought enough time. So next we have Chao talking about near light photometric stereo using circularly placed point light sources without deep neural nets.
Thanks for the introduction. So I'm Chao Liu. I'm from Carnegie Mellon University. It is my great pleasure today to introduce my work on the near light photometric stereo using circularly placed point light source. So this is a joint work with my advisors, Srinivasa, Narasimhan, and Artur Dubrawski. So the circularly placed light sources are very commonly used in the real world because first, they are portable, and second, they are easy to manufacture. For example, in the surveillance camera, we can often find a ring of NIR LEDs around the camera to provide illumination in the dark. Also, in the medical imaging systems such as the endoscope and dark field imaging, we often can mount a LED ring on top of the device to provide the illuminations because of the small dimension. Also, in portrait photography, we often use a ring of LEDs to provide illuminations for the face in order to avoid cast shadows. And those light sources could be very useful if we have the control over the light source position, either by turning on and off the LEDs at different positions or change the lighting position mechanically. For example, if the point light source is placed very close to the object, then by using the near light photometric stereo, we can reconstruct the shape of the object. If the point light source is put pretty far away from the object, then we can assume the incoming light source is parallel to each other. And under this assumption, people before have shown that we can do the BRDF invariant shape analysis even without knowing the BRDFs. And apart from recovering the shapes of the object, a similar approach was used before to detect the depth edges in a scene from the images captured with different light source conditions. So here, we will focus on the near light photometric stereo using a ring of LEDs. More specifically, we will focus on the in a setup where the ring of LED is very small, such that the light source baseline is very small. And the near light photometric stereo is not trivial. So let's first look at the distant light source condition. We can assume both the intensity and direction coming from the light are constant across all the scene points. However, for point light source, this is not the case. The readings coming from the light source falls off with the distance between the light source position and the illuminated scene point. So the incoming lighting direction is spatially variant. Also, because the light directions are not parallel to each other, the incoming light source direction changes for scene points and different 3D locations. Another difficulty comes from the small light source baseline. Here, we show a sequence of images captured with an LED ring with 30mm radius placed around the camera. And the object is placed around 400mm away from the camera and light source, which is more than 10 times larger than the radius of the LEDs. As we can see, due to the very small ratio between the light source baseline and the object distance, the change of the image intensity is quite small. Due to the near light condition and the small light source baseline limitation we mentioned above, it is not straightforward to estimate the 3D shape from the images. The second image shown here is a reconstruction using the decent light source assumption. Because we haven't considered the spatially variant nature of the incoming light source direction and intensity, the reconstructed shape is highly distorted. The third and fourth column in the image shows the reconstruction using the method proposed by Kuo and his colleagues last year. They formulate the problem in the near light condition. But as we can see, the vinyl reconstruction is very sensitive to the initial depth guess. Even if the initial depth is very close to the true depth of the object, we can see the lower part of this reconstruction is not right. Instead, our method can deal with both the near light condition and the small light source baseline limitations. So before going into our method, let's quickly revisit the photometric stereo. So by assuming decent light source, the light direction across the scene are parallel and constant. Assuming the scene is Lambertian, the image intensity for the scene point is a dot product between the light source direction and the surface normal of the point, scaled by surface albedo. But for a near-field point light source, this is not the case. Instead, for a point on the surface, the incoming lighting direction undergoes an inverse square fall-off. This is described by this first term. Also, the incoming direction depends on both the light source position and the scene point position. More generally, for projective camera model, given the projection of the scene point, if we know its corresponding depth and the camera intrinsic matrix, we can back project the pixel from the image domain back into the 3D space and got the 3D position of the scene point location. So in summary, for a scene point illuminated by a near-field point light source, its image intensity is a function of the surface albedo, the light source position, camera intrinsics, and the depth and surface normal of the point. As we can precalibrate the light source position in the camera, the sets of unknowns are surface albedos, depths, and surface normals. So we can divide the near light photometric stereo into two kinds. One is to solve for the surface normal and depth separately, and then combine them using some smoothness constraint, such as the integrability. But in the real world, the surface normal is fully determined by the depth. So another kind of method instead solve for the depth directly. In this method, the surface normal is represented as a function of the depth. More specifically, it can be represented as the normalized first-order partial derivative of the depth. However, for projective camera model, the relation is non-trivial since both the x and y coordinates of the scene point depends on the depths themselves. So in this work, we are going to solve for the depths directly using near light photometric stereo. But instead of representing the normal in a differential form, we aim to represent the surface normal in terms of the depths in a more tractable manner. So in the image domain, we can treat the pixels as nodes on a regular mesh grid. And we can triangulate the 2D mesh grid plane and define the ring 1 neighborhood of the pixel to be the pixels sharing the same edge. Given the depth and the camera intrinsics, we can back project the nodes into a 3D space. And for pixel and its surrounding neighborhoods, we can get its corresponding 3D mesh. And we can borrow the definition of phase normals and vertex normal from the graphics community, where the phase normal can be computed very easily by crossing product the two edges of the face. And we define the surface normal of the point to be the vertex normal in the 3D mesh, in the 3D space. In this case, the vertex normal is a weighted sum of the phase normal surrounding it. And in this way, we can represent the surface normal for a pixel in terms of the depth of itself and the depth of its surrounding pixels. Okay, so in summary, we define the surface normal as a vertex normal after back projecting the pixels into a 3D space. Given the captured image, we can optimize the depths and surface albedos by minimizing the difference between the photometric difference between the measured image and the modeled image. And we also add one regularization term for the depths. But given the highly non-convex and nonlinear relationship between the image intensity and the scene depths, the optimization of the depths can be easily trapped in a local minimum. Here in the first row, we show two images captured using the LED ring with 30 millimeters. And in the second row, we show the final reconstructions with different initializations. As we can see, if the initialization is far from the true depth, we are still suffered from the incorrect surface reconstructions. So, a good initialization of the depth values at vertices is very crucial for us to avoid being trapped in a local minimum. So, to get a very good initialization for depths, we propose to use the differential images. The differential image is a difference of images captured with adjacent light source turned on. To make this differentiation valid, the distance between the adjacent light sources should be very small. And this requirement can be easily satisfied by using a very small baseline light source. So for point light source, we can model the differential image by taking the derivative of the image intensity with respect to the LED index. And we have derived in the paper that this differential image can be decomposed into two terms. Basically, the first term describes the intensity change contributed by the change of incoming light direction. And the second term describes the intensity change contributed by the distance change. Because the lights are mounted on a circular LED ring, so the light source position and the light source motion direction are perpendicular. So we can remove the dot product between them in the second term, shown in the first line. And let's look at the simplified second term. So the dot product with the differential motion vector is small, and it is further attenuated by the distance between the light source and the point. So we can ignore the second term for the case of depth initialization. So here, intuitively, what we here assume is that for depth initialization, we can approximate the differential image to be caused by only the change of incoming light source direction. Now, we can initialize the depth based on the approximated differential image model. Compared with the raw image formation model, by using the differential images, we are free from estimating the surface albedo. Another advantage is that there is no inverse square attenuation term, so the error function is less nonlinear. So those two benefits can help us to get a good initialization for depth. To summarize, we propose a two-stage algorithm for near-light photometric stereo. In the first stage, we use the differential images to initialize the depths. In the second stage, given the initialized depths, we can refine that using the original images and the original image formation model to get the 5D, 3D reconstruction. So here we show the performance performance with respect to different initial guess in simulation. The performance is measured using the average error in the surface normal estimation. In the simulation experiment, we initialize the scene as a plane parallel to the image plane at different depths. We compare our method with a method proposed by Kuo and his colleague, where a variational approach was used to optimize the depths directly. As shown, our two-stage algorithm is more robust to the initial depth guess, even if it is very far away from the depth values. So in the experiment, we use an LED ring placed in front of the camera as a light sources. And the radius of the LED ring is 30 millimeters, similar to the dimension used in a lot of commercial surveillance cameras. And there are 24 LEDs mounted on this LED ring. And it can be controlled individually by using our Arduino board. So as the light source baseline is very small, and we will use the differential positions of them, we need a very accurate calibration for their positions. Traditionally, the light source positions can be calibrated using a chrome sphere. However, for a small baseline light source, the reflections on the sphere, as shown in the figure on the right, is very converged on the sphere surface. So by using this kind of reflections, it is very error-prone to get the light source positions. So instead, we use a specular monitor to calibrate the light source. We capture two sets of images. First, we turn off the LEDs and display a checkerboard pattern on the monitor. After capturing several orientations of the monitor, we can use an off-the-shelf camera calibration toolbox to get the orientation of the monitor and their positions. And for each orientation of the monitor, we turn off the display and turn on the light source on the LED sequentially and capture the reflectance of them in the image. So given the camera intrinsics and the orientations of the monitor and image coordinates of the reflected light, we can use the ray trace and triangulation to find out the final estimation for the light source positions. So here, we compare the calibration accuracy for method using our method and using a chrome sphere. As shown, the position of the light sources are located much accurately by using our method, especially in the Z direction, the depth direction. So given the calibrated light source position, we can reconstruct the object using a two-stage photometric theorem we just talked about earlier. Here we show the input images and the reconstructions in different stages. So note that even the input image change is very small across different LED light positions, we are still able to reconstruct the depth variation and the surface details in the 3D space. And also note that the reconstruction using the differential image is noisy, but it captures overall depth variations, which is more important in the second stage. Since the noises in the reconstruction from the first stage can be removed by using the original image. And then I got brave enough to reconstruct my own face. So the reconstruction is good overall, except for the regions with a lot of specular reflections, such as my forehead and the top of my nose. So for those regions, the image intensities are dominated by the specular reflections for all the images. And we have not considered the non-Lambert reflectance here. So that's why the reconstruction there is not good. So this could be one of our future directions to look at. And we want to generalize our method to deal with this kind of situations. So in summary, we propose an algorithm for near-light photometric stereo using circularly placed point light sources with small baselines. And we choose to use the mesh representation to model the relation between the depth and the surface normal. Then we'll propose a two-stage algorithm, where in the first stage, the depths are initialized using the differential images, and the second stage, the initial depth is refined using the original images. And here are some future work directions. So one is to use our method for surface materials with subsurface scattering. Because we are using the differential images and the global illumination between the global illumination components for two images that are captured using very nearby light sources are very similar. So by taking the difference of them, we can get rid of most of it. So this could be useful for human skin imaging under near IR light, near infrared light. And we can, as we said before, we can take into account the surface BRDF if the surface material is not Lambertian. And finally, it is very interesting to look at the BRDF environment shape analysis using the differential images, as has been done several years ago for the distant light source case. So this concludes my talk. Thanks.
Thank you, Chao. Questions? Yes, go ahead.
I find the reconstruction quality very impressive. How many images do you capture?
There are 24 LEDs mounted on the light source, so we capture 24 images in total.
Do you have a sense for how the reconstruction quality would degrade as you lower the number of images?
Yeah. We did that in the simulation, and we found that for this ratio between the light source baseline and the distance, the accuracy will saturate above 10 LEDs. And we also mentioned that in the paper.
And these are uniformly distributed 10 LEDs. Are there any benefit to having vertical or horizontal bias to the positions?
Here we only consider the uniform distributions, but as long as the distance between the LEDs are small enough.
Okay, because I think you're dependent on the differential images.
Right.
So they can't be too far away.
Yeah,
from each other.
right, exactly.
Okay. Question here?
You get a very non-uniform light when you pass it through a surface with the LED and the packaging. So if you've got a lens like the security camera one, you've got a spherical lens, you'll actually cast an image of the LED dye.
I see.
And you'll see a square bright patch with a multiplier, or a hole with a multiplier right next to it. You can see the multiplier. So if you're using that as you're assuming it's a point source, you're
Yeah.
actually not going to project another image. The LEDs you were using are actually very good for this because they're flat top.
Yes.
You've got no lensing, so you've got it's almost like a point source,
Yeah.
but you do have some
Yeah.
reflective behavior because you've got downward and upward emissions of the dye that creates non-uniform.
Right.
So the question is, what if the light distribution from LED is non-uniform?
Right. So we initially built the prototype using just the LED. You mentioned there is a curvature on top of the LEDs, and as a result, the light source intensity distribution over the angles is not uniform. So in that case, the traditional approach to do that, I also try that, is to change the point light model. So in the point light model, the intensity first lower the distance in a square form, right? So in that case, we also can add another term, which is dot product between the perpendicular direction of the LED and the angle we are looking at, and it will decrease the value when this angle increases. So this can kind of calibrate for this effect, and that function can be calibrated. But here we didn't consider that effect for simplicity.
Go ahead.
Larger scene. So the scene.
Can you repeat the question?
The question is, did I try a larger scene? So
You mean a more distant scene?
yes.
Yeah.
So the
Okay.
you mean the depth variation is large?
No, he's saying at the same about 200 millimeters that you had, if you had a much bigger object. But I guess you need a wider field of your camera. But
Yeah. So that will become out of field of view of the camera. But in terms of the distance of the object, this algorithm in real world works up to 600 millimeters with a LED ring of 30 millimeters away. And so the limitation for that is that the LED light intensity here we're using is not bright enough As a result, if the object is placed very far away from the camera, then the differential image, it will be saturated with a noise because because the lighting direction and the distance change across different LEDs is too small for a very far away object. So I think the one solution would be either using a brighter LED or using a kind of larger baseline.
Excellent. We're out of time, but thank you so much. Beautiful results for everyone. Thanks a lot.
I need display port. So while we are getting set up, I know I had this wonderful idea for closing out this conference. I was going to ask all of you for keywords that you learned for the first time in this conference, but damn it, Ramesh beat me to it. Anyway, kidding aside, I hope you all had a fun time. At least as much fun as we had putting the conference together, the program together, and getting all the work done. I have to, while we are closing the conference, I have a bunch of people to thank. My program chairs, the organization team, volunteers, support staff, speakers, session chairs, and of course, the posters, demo people, and all of you as audience. But I decided to just thank one person, just isolate one person and thank her, and that's Kimmy, right? So let's have a round of applause for Kimmy. You don't escape so easily, right? So Kimmy put in a lot of effort right from the beginning all the way to the end. She's still taking photographs. And I think in many ways I was far less stressed out. I had a lot more sleep thanks to her presence and her contributions to the community. So Kimmy, on behalf of the ICCP community, a big thank you. Okay, now we have the announcement for the best paper, best demo, and the best posters. I'll hand it over to my co-program chair.
Yeah, hello. I'm Ravi Ramamurthy from the University of California, San Diego. I'm one of the program chairs here. So I was in charge of choosing the best paper, and for this purpose, I assembled a committee consisting of Wolfgang Heidrich and Olli Kossert. And we have designated Wolfgang as the chair of the committee, so he is actually going to describe the process and announce the best paper, just to create a little bit more excitement.
Okay. Thank you, Ravi. Just go to... Okay, so Ravi already outlined the process. So essentially, as you know, we have a double-blind peer review process for all the papers. And then, of course, Ravi and the other paper chairs were responsible for making final decisions for the acceptances. And at the same time, they prepared a short list of papers for us to be considered for the Best Paper Awards. And then the committee that you see here, again, looked at those papers, read the reviews, had a discussion, and then came up with a final decision for the Best Paper Award. Okay, this process was also double-blind, just like the initial paper review. So the only people in the whole process who knew the author names were actually the paper's chairs. Okay, so without further ado, I want to announce the paper. The paper is actually that we chose is a paper that makes interferometry more robust to ambient light by basically combining phase shift interferometry and dynamic interferometry. What we liked about the paper is that it had really interesting combination of a lot of things that are relevant in computational imaging. So there's a very thorough joint image formation model for these approaches. There's a careful design of a prototype and a very good implementation of that prototype, and then a thorough evaluation of the experimental verification of the system. And so I'm happy to announce the paper. If the authors are, I know there's one author here in front, but I'm sure are your co-authors still here? Yeah. Please come here. Yeah. Yeah, all of the authors actually. Let's bring all the authors on to the front. All the remaining authors that are still here. Yeah. Okay. Okay, that's it from me. Thank you.
All right, so I'm Matthew O'Toole, and I'll be presenting the Best Demo Award. So we had a lot of great participation this year. So we had around 50 posters and 11 demos, I think, in the end. And we had about 100 people that voted in, so this is a purely democratic process. I had no decision in matter. And I'd like to announce the best demo now. The best demo for this year will go to Chi Guo, Emma Alexander, and Todd Zickler for their demo on focal track. Depth and accommodation with oscillating lens deformations. There, and they're coming down.
I'm Sanjeev. So now we'll have the best poster. And the best poster is occluder-aided computational periscopy, Sheila Worth, John Murray Bruce, Yanting Ma, Charles Saunders, Christopher Yu, Bill Freeman, and Vivek Goyal. So any of the authors here, please come up.
We are almost done. The last bit of the program is a short presentation by the chairs of the organizers of ICCP 2019. So ICCP 2019 will be organized in Tokyo, and 2020 will be in St. Louis. So the last bit of the program is the chairs of 2019. They want to make a short presentation about what they have in mind.
So I'd like to introduce the next ICCP 2019. So I'm Yasuhiro Mukaiga from NICE in Japan. So as you know, this is a history of the ICCP. The first ICCP is held at San Francisco in 2009. So every year, so ICCP is held in the, some cities. Now we are in Pittsburgh. So this ICCP is a very memorial ICCP because this is the 10th anniversary. Congratulations. So, but ICCP is an international conference. So next we move to the outside of the United States. So next ICCP is the first ICCP held outside United States. So we move to Tokyo in Japan. So do you know the location of the Tokyo? Here is the Tokyo. So we have a next ICCP in Tokyo. So there is a May 15 to 17, and venue is a Institute of Industrial Science in the University of Tokyo in Japan. So these are team members. I will serve as the general chair. So program chairs are Hajime and Mohito and Matthias. And publication chairs are Jean, Francois, and post and demo chairs are Yashuki and Jingi. And industry chair is Shinsaku, and finance chair is Takuya and Aswin. And web and social media chairs is Hiroyuki, and local arrangement chair is Yoichi. This is our current members. So we will our best for the success of the next ICCP. So Tokyo, in the Tokyo, there are two major airports. One is Narita International Airport, and the other is Haneda or Tokyo International Airport. So there are many direct flights from the United States, and it is not so far from the venue. And the venue, Tokyo University, is very near from the center area of the Tokyo, so you can visit a lot of sightseeing spots, including Meiji Jingu, Imperial Palace, and Akihabara is very famous for the Japanese pop culture such as manga, anime, and cosplay. And you can enjoy the Ameoko markets and Tempura Sky, Tokyo Sky Tree. And if you have any time, so you can visit the Kabuki Theater and small arena. Please enjoy the Tokyo. So please visit our website. So the link will be shown in the current ICCP 2018 page soon. So, but please be careful for the fake site. If we search the Google by word of the ICCP, I found this fake page. This is not a perfect fake page. So, but this is a international conference of competence photography in Kyoto. This is a fake. Please be careful. Please follow the through link here. So, okay, let's meet at Tokyo. Thank you.
Thank you, Yasu. Let me keep it short. Shashiburi and sayonara.